The topic is sequential approach of limit. We have already learned about the epsilon delta concept of limit. Now we need to link the limit concept and the sequence concept. That is, what is the relation between a sequence and the limit of some function. So starting with a theorem. Let f from a to r be a function and c be a limit point and c be a limit point of a. Then limit extending to c fx equals L if and only if for every sequence xn in a converging to c in bracket xn not equal to c for all n belongs to natural number, xn in a converging to c, then f of xn should converge to L. Then we will say that under the point extending to c, the limiting value of the function fx will be L. And the concept is, or the condition is, whenever we get a sequence xn which is tending to c, then this should imply f of xn should tending to L. This is the concept. If this happens, then we will say that this is the sequential approach of limit. Under this definition, the limit will be L. And if it doesn't happen for at least one sequence, then we can, from there we can easily claim that the sequence that the limit is not going to L. So this theorem is actually using to disprove something. That is, as you can see from the concept, that is, it is true for every sequence. Now it is almost impossible to find out every sequence from a set. So we can use this concept just to disprove this. That means some L is not a limit of a function, or the function is not a convergent function. This is the divergent one. So to prove this one, we need the divergent criteria of the same theorem. That is, this is the convergence criteria. When we will say that the function is convergent to that limit. If for every sequence xn tending to c, if f of xn tending to L, then it is. And what will be its concept? That at least we can found at least one sequence for which xn is tending to c, but f of xn is not tending to L, right? So this is called the divergence criteria of sequential approach of limit. Let at first state the criteria, then we will use it to solve the problems. It is saying that when we will say that a function limit extending to c fx is not equal to L, when we can say? We can say if there exists a sequence xn which is tending to c, but f of xn is not tending to L, right? So this condition is to disprove something. That is, whenever we are trying to prove that the L is not the required limit, then we can use this divergence criteria. This is very much useful in problem solving. And there is also another one divergence criteria which we can also use, which states that if there exists two sequences xn, yn, such that xn is also tending to c and yn is also tending to c, but they are not tending to but their functional sequence is not tending to the same limit. That is, by taking xn and yn, if we find two sequences, if xn which is tending to c and yn which is tending to c, but f of xn does not tending to L or f of yn does not tending to L. That means they are tending to the same limit, but their functional value sequences f of xn and f of yn is not tending to the same limit. They are not tending to. then we can also say that the limit is not L. Okay, so these are two criteria for disproving something. So to finding the divergence concept of the limit. Now we will take few examples. I'll give you the functions. You have to apply this divergence criteria, either this one or this one, to prove that the limit either does not exist or not tending to that particular point L. Okay. So at first, the first example is example number 1. Prove that limit extending to 0 1 by x does not exist in R. We all know that this doesn't exist, because 1 by undefined quantity, 1 by 0 it becomes undefined. We all know that, but we have to prove that using this sequential approach of limit functions. Okay, prove that limit extending to 0 1 by x does not exist in R. That means if we want to apply this sequential criteria, what we have to find? We have to find a sequence xn which is tending to C. That means this 0, C is our 0 here. But f of xn is not tending to any finite quantity. Right? This is our divergence criteria, or we can use the second divergence criteria is also, whichever is applicable here. So I'm starting to find by applying the first divergence criteria. That means we have to find one sequence xn which is tending to 0, but the limiting value sequence f of xn is not tending to in any finite quantity. So what will be the xn? Let xn equals 1 by n. It means I am considering the sequence 1 by n, which is 1, then half, then 1/3, 1/4. You all know the limit of the sequence. The limit is 0. That means xn is tending to 0. Now what about f of xn? F of xn means f of 1 by n. And what is our fx? Fx is 1 by x. So what will be the value of f of 1 by n? It will be 1 by n, that is n. Now check this sequence. We all know about that sequence n. Does it converge to a finite limit? The answer is no, because it's an unbounded sequence. Unbounded sequence is not a convergent one. So this does not converge to any finite limit. That means by using the divergence criteria, we get one sequence which is 1 by n and which is tending to 0, but f of 1 by n, which is equals n, is not tending to any finite limit. That means the limit of this one extending to 0 1 by x does not exist. Okay. Moving to the next example. Next, I am introducing a new type of function which is called signum function. And it is denoted by SGN x, and we did it as signum function, and it is defined by this one, x by mod x when x not equal to 0 and 0 when x equals 0. This is signum function. Now if you expand it a little bit, x not equal to 0, that means either x greater than 0 or x less than 0. Now whenever x greater than 0, what will be the value of mod x? It will be x, that is it will be x by x, that means 1. And whenever x is less than 0, the value of mod x will be minus x, so which will be x by minus x, that means minus 1. And when x equal to 0, it is given the value is 0. Sometimes we also write signum function like this also. That is this one and this one. These are the same, actually the same definition of signum function. For x greater than 0, it takes the value 1. For x less than 0, it takes the value -1. And for x equal to 0, it takes the value 0. We have to prove by using sequential approach of limit that limit extending to 0, signum x does not exist. We have to prove it. Now we already know how to prove the limit by using left hand condition and right hand condition, right hand limit and left hand limit, using the 12th standard conditions. We all know how to do that. Just by taking limit extending to 0 plus signum x and then limit extending to 0 minus signum x. Both are not equal because for 0 plus it takes the value 1 and for 0 minus it takes the value -1. So these are not equal, so limit does not exist. That was the previous concept. Now we have to use the sequential approach. That means we have to find out at least one sequence xn, right, which is tending to the quantity 0, but f of xn does not tending to any certain finite quantity, right? This one. If we can prove this, then our work will be done. So what will be the sequence xn, which is tending to 0, but their functional value is not tending to any finite limit. I am considering the sequence xn equals -1 whole to the power n by n. This one, this sequence. What will be the values of this sequence? If you put the value of n one by one, it will be at first -1, then half, -1/3, 1/4, -1/5, and so on. What will be the limit of that sequence? It is tending to 0. We all know that. This is a very common example in the chapter of sequence. So this is tending to 0. Now what will be f of xn? F of xn is our signum function, right? So signum of this quantity, -1 whole to the power n by n. Now signum function always depend on that positive quantity we are taking or negative quantity we are taking or 0 quantity we are taking. So whenever this n is positive, then what will take the value? What will be the value? If n is positive or n is even, not rather, actually n is always positive because we are considering the natural number. So whenever n is even, then the whole quantity is positive, right? If you put n equals 2, 4, 6, 8 and so on, that means whenever n is even, then this will become 1 by n plus 1 by n. So for that reason, the signum value will take the value +1, because this is the definition of signum function. And whenever n is odd, it will take the value -1 by n. That is -1, -1/3, -1/5 and so on. So it becomes negative quantity, then signum function will take the value -1. Right? That means we get the sequence as 1 when n is even and -1 when n is odd. That means this sequence f of xn can be written as -1 whole to the power n. Right? This sequence. Now tell me what will be the limiting value of this sequence. We all know that this sequence is a divergent sequence. Rather, it's a oscillatory sequence which oscillates between -1 to +1. So this is not going to a finite quantity. That is, we get one sequence xn which is tending to 0, but f of xn is not tending to a finite quantity. So by using the divergence criteria of sequential approach of limit, we can say limit extending to 0, signum x does not exist. Does not exist. Okay. We can show the same thing, that is signum function's divergence criteria, by using the second concept of divergence criteria also. What was the second concept of divergence criteria? The first concept was if xn tending to c and n does not tending to L, then we can say the limit is divergent. And the second criteria was we have to find out two sequences xn and yn such that xn tending to C and yn tending to C, but f of xn and f of yn, they are not tending to the same limit. These sequences are tending to same limit, but their functional values are not. So if we want to apply this concept over the same function, that is signum x, what will we take? We have to find out two sequences xn and yn. What will be these two sequences? Such that they are tending to the same limit, but their functional values are not tending to the same limit. Just think a little bit, it's very easy. If we take xn equals 1 by n and yn equals minus 1 by n, then xn is tending to 0 as n tending to infinity, and yn is also tending to 0 as n tending to infinity. But what about f of xn? This is all positive quantity, so signum function, that is f of xn, will take the plus 1 value, so it will plus 1. And f of yn, these are all negative value sequences, so signum function will take the minus 1 value for negative quantities, so this will be minus 1. That is f of xn is tending to 1 and f of yn is tending to minus 1. That means they are not tending to the same limit. So signum function's limit does not exist. Okay. It does not exist. So we can use any two of the concepts to disprove that some limit doesn't exist. This criteria is basically used to disprove something. Now moving to the next example. Prove that limit extending to 0 sine 1 by x does not exist. Prove that limit extending to 0 sine 1 by x does not exist. In R, obviously. We are talking about real analysis. Here also we have to find out two sequences xn and yn such that both are tending to 0, but f of xn and f of yn are not tending to the same limit. So what will be the values of that xn and yn? I am taking xn equals 1 by 4n plus 1 into pi by 2, this sequence, and yn equals 1 by 4n minus 1 into pi by 2. Now what will be the limits of these two sequences xn and yn? This is obviously tend to 0 as n tending to infinity, and this is also tending to 0 as n tending to infinity, xn and yn. Now let's check the value of their functional sequences, that is f of xn. What will be f of xn? It will be sine 1 by xn, right? That is sine 4n plus 1 into pi by 2. What are the values of sine 4n plus 1 into pi by 2? Put the value of 1 n by n with the values of n 1 by 1, you will get the value. If you put n equals 1, it will be 5 pi by 2, which takes the value 1. Then put n equal to 2, you will get 9 pi by 2, which also takes the value 1. Then put n equals 3, you will get 13 pi by 2, which also takes the value 1. That is, ultimately the value is 1. So this sequence is converging to 1. Now find out f of yn. So f of yn is sine 1 by yn, right? Sine 1, that means 4n minus 1 into pi by 2. Now put the values 1 by 1. At first 3 pi by 2, which is equals minus 1. Then put n equal to 2. It will become 7 pi by 2, which is again minus 1. Then put n equals 3. It will become 11 pi by 2, which is again minus 1. So the ultimate value is minus 1. That means we get two sequences xn and yn. They both are converging to 0, but f of xn converging to 1 and f of yn converging to minus 1. Two to different limit. That means by using the second concept of divergence criteria, we can say limit extending to 0 sine 1 by x does not exist. Okay. This is a very important example. That is, limit extending to 0 sine 1 by x does not exist. We can prove it by applying any 4-5 methods also. This is one of the methods to prove it. Okay. So the next example is prove that limit extending to 0 cos 1 by x also does not exist. This will be your homework. You have to find out two sequences xn and yn, just like the previous one. You have to find it out. For the previous example, sine 1 by x, you can take another set of x and yn also. There are many more examples of x and yn, such that x and yn tending to same limit, but their functional values aren't going to the same one. Okay. So I am taking that 4n plus 1 into pi by 2 and 4n minus 1 into pi by 2. You can take another set of examples also. So similarly, for cos 1 by x, we have to find out the same thing. This will be the homework. Okay. So you have to find out two sequences xn and yn such that both are tending to 0, but their functional value sequences fx and fyn, they are not tending to the same limit. Okay.